Hi, I would like to present our paper about the interactive rendering of shadows, illuminated from textured polygonal light sources, and environment lighting as shown in this slide. The authors are Hiroki Okuno and Kei Iwasaki from Wakayama University, Japan. This is the real-time captured animation of our method. Our method can render plausible shadows under a textured polygonal light source and environment lighting at interactive frame rates. In addition, our method can express various appearances from metallic to rough surfaces using physically based GGX microfacet BRDFs. In this presentation, we will focus on the explanation for the polygonal light rendering, and that for the environment light rendering can be found in our paper. Despite recent progress in area light shading, efficient rendering of shadows under polygonal area light sources with physically based materials remains a challenge. In previous approaches for polygonal light shading, the reflected radiance can be calculated by the integral of the cosine-weighted BRDF FR tilde over the entire polygonal domain. Since the cosine-weighted BRDF is well approximated with a spherical distribution that has a closed-form solution of the boundary integral along the polygonal edges, this integral can be efficiently calculated, enabling real-time performance. To render shadows, however, the visibility function V must be considered, and it can mask a fraction of the integral domain, as shown in this slide, making it difficult to apply the boundary integral along the polygonal edges. Previous methods use spherical harmonics to represent the visibility function or stochastic sampling with denoising to render shadows from polygonal light sources. Wang et al. Derived an analytic solution of the integral of spherical harmonic functions over the polygonal domain. Wu et al. Accelerate the computation of the spherical harmonic coefficients for polygonal light sources using gradients. Although these methods can render shadows for both polygonal light sources and environment lighting, these methods require costly triple product integral of spherical harmonics and can be inefficient for highly glossy BRDFs as they require higher order spherical harmonics to represent such BRDFs. Heitz et al. Proposed a ratio estimator to add shadowing effects by stochastically sampling a small number of shadow rays, then the rendering results are denoised. Although this method can render plausible results in some cases, this method suffers from a lack of shadows and blurred shadows as shown in this slide. The basic idea of our method is to partition a polygonal light source into a set of polygons entirely visible from each vertex, and a set of polygons partially occluded from each vertex. We do not consider entirely invisible polygons since they do not contribute to the reflected radiance. If we partition a polygonal light source P into an entirely visible polygon P1 and partially occluded polygon P2, the product integral of the BRDF and the visibility function over the polygonal light source P is simply the sum of that over P1 and that over P2 as shown in this equation, since the visibility function, V in P1 is constant. The product integral over P1 is reduced to the integral of the BRDF over a polygonal domain that has an analytical solution of boundary integral. The partially occluded polygon P2 is further subdivided into the entirely visible polygon P3 and the partially occluded polygon P4 as shown in this slide. By repeating this process, the polygonal light source can be partitioned into a set of entirely visible polygons and a set of partially occluded polygons. The former sum can be calculated analytically by using the boundary integral. On the other hand, the latter cannot be calculated analytically, due to the visibility function that returns either 0 or 1. Our method approximates the double product integral by factoring out the visibility function at the cost of the approximation error, where Vj bar is the average visibility over the partially occluded polygon Pj. Our method can reduce the approximation error so as to partition the polygonal light source into the entirely visible polygons as much as possible, and to reduce the partially occluded polygons. To partition the polygonal light source into the entirely visible polygons and the partially occluded polygons, we first precompute the visibility function v at each vertex, and the visibility function is stored at each cube map face as shown in this slide. Our method represents the visibility function at each cube map face with a binary space partitioning visibility tree, BSPVT for short. BSPVT partitions a set of pixels in each cube map face into groups of pixels with similar visibilities. Each inner node of BSPVT corresponds to a 2D splitline that partitions a set of pixels into two disjoint sets. Since the left side pixels with respect to the red splitline have the same visibilities, these pixels are considered as a leaf node as shown in this slide. In a similar way, the right side pixels are further partitioned into two sets of pixels by using the green splitline, and two leaf child nodes are constructed as shown in the right. We now explain how to construct BSPVTs. To construct BSPVTs, our method finds split lines by minimizing the error function E as shown in this slide. In this equation, dPL indicates the signed distance function from the split line L to the pixel P. H0 is the heaviside function that returns 1 if the argument is greater than 0, and returns 0 if the argument is negative. Therefore, this term returns 1 if the pixel P is in the right-hand side of the splitline L, and returns 0 otherwise. This term represents the visibilities defined by the splitline L. So this subtraction indicates the difference between the visibility defined by the splitline and that stored at the pixel P. In summary, the error function E counts the squared number of pixels having different visibilities defined by the splitline, as shown in the blue areas in this image. Minimizing the error function E leads to finding the splitline so that the visibilities defined by the splitline match the target visibilities. By minimizing the error function E using Nelder-Mead method, the parameters of the splitline L0 are obtained and stored at the inner node of the BSPVT. The set of pixels P is partitioned into P1 and P2 using the splitline L0. Then the average visibility and the variance of visibilities are calculated at P1 and P2. Since the variance of visibilities in P1 is 0, in this case, we terminate partitioning and store the average visibility at the leaf node. Our method finds the split line L2 that separates the set of pixels P2 by minimizing the error function E. Our method repeats this process to construct the BSPVT. I would like to show the visibility function defined by BSPVT. The left image is the original visibility function, and the right image is the visibility function defined by BSPVT. As shown in this slide, our method can represent complex visibility functions very well with BSPVT. To render a scene using BSPVTs, the polygonal light source is projected onto each face of the cube map. Then our method subdivides the projected polygonal light source by traversing a BSPVT. The projected polygonal light source is subdivided by the split line associated with each inner node. If a leaf node with non-zero average visibility is reached, the reflected radiance due to this subdivided polygonal light source is calculated by using the associated average visibility. By repeating this process, the reflected radiance is calculated. Now I would like to show some results. This slide shows the statistics of BSPVTs for 3 scenes including the number of vertices, rendering frame rates, the precomputation time, and the storage size. Our method achieves about 11 to 83 FPS in these scenes. The precomputation times for BSPVTs are less than 50 minutes. and the storage sizes for BSPVTs are less than 600 megabytes in these scenes. This slide shows the comparisons between our method, the stochastic sampling method proposed by Heitz and colleagues, and the spherical harmonics-based method proposed by Wang and colleagues. From left to right, each column corresponds to the reference, our method, Heitz 2018, and Wang 2018. The right three columns show the difference between the reference and each method. The number under each image indicates the render times or the RMSE errors. Alpha is the roughness parameter of the GGX microfacet BRDFs. As shown in this slide, our method outperforms two previous methods in terms of the render times and the accuracies for various materials, from top to bottom, highly glossy surfaces to diffuse surfaces. This slide shows comparisons between our method and the spherical harmonics-based method with different orders from 4th to 16th. Although the spherical harmonics-based method can reproduce specular highlights and complex shadows by increasing the order, it also increases the render time due to the costly triple product integral. Therefore, Wu and colleagues band-limited the lighting and the visibility function spherical harmonics coefficients with 4th order, and BRDF spherical harmonics coefficients with 8th order to achieve real-time performance, which can fail to reproduce specular highlights and high-frequency shadows on the floor as shown in this slide. Our method can reproduce specular highlights and shadows on the floor similar to the reference at interactive frame rates. This slide shows a real-time captured animation of the living room scene. Our method can manipulate the polygonal light source in real time, including the translation, rotation, scaling, and texturing as shown in this animation. Although our method can render all frequency shadows at interactive frame rates, our method has several limitations. Our method assumes static scenes to precompute the visibility function at each vertex, while the previous method proposed by Heitz and colleagues can handle dynamic scenes. Our method calculates the reflected radiance per vertex. Therefore, our method requires sufficiently tessellated meshes. Currently, our method is implemented on a multi-threaded CPU. Let me conclude my presentation. We have proposed a geometric approach to adding shadowing effects for polygonal and environment light rendering. Our novel visibility representation, BSPVT, enables us to render all frequency shadows with all frequency BRDFs. Our method allows dynamic viewpoint, BRDF, lighting as shown in the real-time captured animation. In future work, we would like to lift the limitations described before. I would like to acknowledge the funding agencies, reviewers, and my former student. That's all and thank you for your attention.